workings of our planet requires a basic knowledge of igneous rocks. Igneous rocks and metamorphic rocks derived from igneous parents make up most of Earth's crust and mantle. Thus, Earth can be described as a huge mass of igneous and metamorphic rocks that is covered with a thin veneer of sedimentary rock and has a relatively small iron-rich core. Many prominent landforms are composed of igneous rocks, including volcanoes such as Mount Rainier and the large igneous bodies that make up the Sierra Nevada, the Black Hills, and the high peaks of the Adirondacks. Igneous rocks also make excellent building stones and are widely used as decorative materials, such as for monuments and household countertops. 4.1 Magma, parent material of igneous rock. List and describe the three major components of magma. Our discussion of the rock cycle in Chapter 1 explained that igneous rocks form as molten rock cools and solidifies. Considerable evidence supports the idea that the parent material for igneous rocks, called magma, is formed by partial melting that occurs at various levels within Earth's crust and upper mantle to depths of about 250 kilometers. Once formed, a magma body buoyantly rises toward the surface because it is less dense than the surrounding rocks. Occasionally, molten rock reaches Earth's surface, where it is called lava, figure 4. 1. Sometimes lava is emitted as fountains that are produced when escaping gases propel it from a magma chamber. On other occasions, lava is explosively ejected, producing dramatic steam and ash eruptions. However, not all eruptions are violent. Many volcanoes emit quiet outpourings of fluid lava. The nature of magma. Magma is completely or partly molten rock, which when cooled solidifies to form igneous rocks, composed mainly of silicate minerals. Most magmas consist of three materials: a liquid component, a solid component, and a gaseous component. The liquid portion, called melt, is composed mainly of mobile ions of the 8 most common elements found in Earth's crust, silicon and oxygen, along with lesser amounts of aluminum, potassium, calcium, sodium, iron, and magnesium. The solid components in magma are crystals of silicate minerals. As a magma body cools, the size and number of crystals increase. During the last stage of cooling, a magma body is like a crystalline mush that contains only small amounts of melt. The gaseous components of magma, called volatiles, are materials that vaporize at surface pressures. The most common volatiles found in magma are water vapor, carbon dioxide. B. When magma crystallizes at depth, intrusive igneous rocks form. When magma solidifies on Earth's surface, extrusive igneous rocks form. Figure 4.2. Igneous rock composed of interlocking crystals. The largest crystals are about 1 centimeter in length. Smart figure 4.3. Intrusive versus extrusive. Igneous rocks and sulfur dioxide, which are confined by the immense pressure exerted by the overlying rocks. These gases tend to separate from the melt as it moves toward the surface. As the gases build up, they may eventually propel magma from the vent. When deeply buried magma bodies crystallize, the remaining volatiles collect as hot, water-rich fluids that migrate through the surrounding rocks. These hot fluids play an important role in metamorphism and will be considered in Chapter 8. From magma to crystalline rock. To better understand how magma crystallizes, let us consider how a simple crystalline solid melts. Recall that, in any crystalline solid, the ions are arranged in a closely packed regular pattern. However, they are not without some motion. They exhibit a restricted vibration about fixed points. As the temperature rises, ions vibrate more rapidly and consequently collide with ever-increasing vigor with their neighbors. Thus, heating causes the ions to occupy more space, which in turn causes the solid to expand. When the ions are vibrating rapidly enough to overcome the force of their chemical bonds, melting occurs. At this stage, the ions are able to slide past one another, and the orderly crystalline structure disintegrates. Thus, melting converts a solid consisting of tight, uniformly packed ions into a liquid composed of unordered ions moving randomly about. In the process called crystallization, cooling reverses the events of melting. As the temperature of the liquid drops, ions pack more closely together as their rate of movement slows. When they are cooled sufficiently, the forces of the chemical bonds will again confine the ions to an orderly crystalline arrangement. When a magma body cools, the silicon and oxygen atoms link together first to form silicon-oxygen tetrahedra, the basic building blocks of the silicate minerals. See Figure 3.31, page 92. As magma continues to lose heat to its surroundings, the tetrahedra join with each other and with other ions to form embryonic crystal nuclei. Slowly each nucleus grows as ions lose their mobility and join the crystalline network. The minerals that form the earliest have space to grow and tend to have better developed crystal faces than do the ones that form later and occupy the remaining spaces. Eventually all of the melt is transformed into a solid mass of interlocking silicate minerals that we call an igneous rock. Igneous processes. Igneous rocks form in two basic settings. Molten rock may crystallize within Earth's crust over a range of depths, or it may solidify at Earth's surface. When magma crystallizes at depth, it forms intrusive igneous rocks, also known as plutonic rocks, after Pluto, the god of the underworld in classical mythology. These rocks are observed at the surface in locations where uplifting and erosion have stripped away the overlying rocks. Exposures of intrusive igneous rocks occur in many places, including the White Mountains, New Hampshire, Stone Mountain, Georgia, Mount Rushmore in the Black Hills of South Dakota, and Yosemite National Park, California. Igneous rocks that form when molten rock solidifies at the surface are classified as extrusive igneous rocks. They are also called volcanic rocks, after Vulcan, the Roman fire god. Extrusive igneous rocks form when lava solidifies or when volcanic debris falls to Earth's surface. Extrusive igneous rocks are abundant in western portions of the Americas, where they make up the volcanic peaks of the Cascade Range. Figure 4.4. Mount Rushmore National Memorial. This memorial, located in the Black Hills of South Dakota, is carved from intrusive igneous rocks. 1. What is magma? How does magma differ from lava? 2. List and describe the three components of magma. 3. Describe the process of crystallization. 4. Compare and contrast extrusive and intrusive igneous rocks. 4.1 Concept checks. 4.2 Igneous compositions. Compare and contrast the four basic igneous compositions: basaltic, granitic, andesitic, and ultramafic. Igneous rocks are composed mainly of silicate minerals. Chemical analyses show that silicon and oxygen are by far the most abundant constituents of igneous rocks. These two elements, plus ions of aluminum, calcium, sodium, potassium, magnesium, and iron, make up roughly 98%, by weight, of most magmas. In addition, magma contains small amounts of many other elements, including titanium and manganese, and trace amounts of much rarer elements, such as gold, silver, and uranium. As magma cools and solidifies, these elements combine to form two major groups of silicate minerals. The dark silicates are rich in iron and/or magnesium and comparatively low in silica. Olivine, pyroxene, amphibole, and biotite mica are the common dark silicate minerals of Earth's crust. By contrast, and the Andes Mountains. In addition, many oceanic islands, including the Hawaiian chain and Alaska's Aleutian Islands, are composed almost entirely of extrusive igneous rocks. The nature of volcanic activity will be addressed in more detail in Chapter 5. Rocks that contain at least 45% dark silicate minerals and calcium-rich plagioclase feldspar are said to have a basaltic composition. Basaltic rocks contain a high percentage of ferromagnesian minerals, so geologists also refer to them as mafic. Because of their iron content, mafic rocks are typically darker and denser than granitic rocks. Basaltic rocks make up the ocean floor as well as many of the volcanic islands located within the ocean basins. Basalt also forms extensive lava flows on the continents. Other compositional groups. As you can see in Figure 4.5, rocks with a composition between granitic and basaltic rocks are said to have an andesitic composition, or intermediate composition, after the common volcanic rock andesite. Intermediate rocks contain at least 25% dark silicate minerals, mainly amphibole, pyroxene, and biotite mica, with the other dominant mineral being plagioclase feldspar. This important category of igneous rocks is often associated with volcanic activity that is typically confined to the seaward margins of the continents and on volcanic island arcs such as the Aleutian chain. The light silicates contain greater amounts of potassium, sodium, and calcium rather than iron and magnesium. The light silicate minerals, including quartz, muscovite mica, and the most abundant mineral group, the feldspars, are richer in silica than the dark silicates. Granitic versus basaltic. Compositions. Despite their great compositional diversity, igneous rocks can be divided into broad groups according to their proportions of light and dark minerals. Near one end of the continuum are rocks composed almost entirely of light-colored silicates, quartz, and potassium feldspar. Igneous rocks in which these are the dominant minerals have a granitic composition. Geologists also refer to granitic rocks as being felsic, a term derived from feldspar and silica. In addition to quartz and feldspar, most granitic rocks contain about 10% dark silicate minerals, usually biotite mica and amphibole. Granitic rocks are rich in silica and are major constituents of the continental crust. Smart Figure 4.5 Mineralogy of common igneous rocks, based on Dietrich, Daly, and Larson. 112. A granite is a felsic, coarse-grained igneous rock composed of light-colored silicates, quartz, and potassium feldspar. Bead basalt is a any-grained mac igneous rock containing substantial amounts of dark-colored silicates and plagioclase feldspar. Than 70% in felsic rocks. The percentage of silica in igneous rocks varies in a systematic manner that parallels the abundance of other elements. For example, rocks that are relatively low in silica contain large amounts of iron, magnesium, and calcium. By contrast, rocks high in silica contain very little iron, magnesium, or calcium but are enriched with sodium and potassium. Consequently, the chemical makeup of an igneous rock can be inferred directly from its silica content. Further, the amount of silica present in magma strongly influences its behavior. Granitic magma, which has a high silica content, is quite viscous and may erupt at temperatures as low as 650 degrees Celsius. On the other hand, basaltic magmas are low in silica and are generally more fluid. Basaltic magmas also erupt at higher temperatures than granitic magmas, usually at temperatures between 1050 degrees and 1250 degrees Celsius. Another important igneous rock, peridotite, contains mostly olivine and pyroxene and thus falls on the opposite side of the compositional spectrum from granitic rocks. Because peridotite is composed almost entirely of ferromagnesian minerals, its chemical composition is referred to as ultramafic. Although ultramafic rocks are rare at Earth's surface, peridotite is the main constituent of the upper mantle. Silica content as an indicator of composition. An important aspect of the chemical composition of igneous rocks is silica content. Typically, the silica content of crustal rocks ranges from a low of about 40% in ultramafic rocks to a high of more. Figure 4.6 Granitic versus basaltic compositions. Inset images are photomicrographs that show the interlocking crystals that make up granite and basalt, respectively. 1. Igneous rocks are composed mainly of which group of minerals? 2. How do light-colored igneous rocks differ in composition from dark-colored igneous rocks? 3. List the 4 basic compositional groups of igneous rocks, in order from the group with the highest silica content to the group with the lowest silica content. 4. Name 2 minerals typically found in rocks with high silica content and 2 minerals found in rocks with relatively low silica content. 4.2 Concept checks. 4.3 Igneous textures, what can they tell us? Identify and describe the 6 major igneous textures. The term texture is used to describe the overall appearance of a rock based on the size, shape, and arrangement of its mineral grains, not how it feels to touch. Texture is an important property because it reveals a great deal about the environment in which the rock formed. Geologists can make inferences about a rock's origin based on careful observations of grain size and other characteristics of the rock. 3 factors influence the textures of igneous rocks. The rate at which molten rock cools. The amount of silica present in the magma. The amount of dissolved gases in the magma. Among these, the rate of cooling tends to be the dominant factor. A very large magma body located many kilometers beneath Earth's surface remains insulated from lower surface temperatures by the surrounding rock and thus will cool very slowly over a period of perhaps tens of thousands to millions of years. Initially, relatively few crystal nuclei form. Slow cooling permits ions to migrate freely until they eventually join one of the existing crystals. Consequently, slow cooling promotes the growth of fewer but larger crystals. See a phaneritic texture composed of mineral grains that are large enough to be identified without a microscope. Baphanitic texture composed of crystals that are too small for the individual minerals to be identified without a microscope. Glassy texture. Composed of unordered atoms and resembles dark manufactured glass. Vesicular texture. Extrusive rock containing voids left by gas bubbles that escape as lava solidize. Pyroclastic texture produced by the consolidation of fragments that may include ash, once molten blobs, or large angular blocks that were ejected during an explosive volcanic eruption. Porphyritic texture. Composed of two distinctly different crystal sizes. Smart figure 4.7 igneous rock textures. On the other hand, when cooling occurs rapidly, for example, in a thin lava flow, the ions quickly lose their mobility and readily combine to form crystals. This results in the development of numerous embryonic nuclei, all of which compete for the available ions. The result is a solid mass of many tiny intergrown crystals. Types of igneous textures. The effect of cooling on rock textures is fairly straightforward. Slow cooling promotes the growth of large crystals, whereas rapid cooling tends to generate small crystals. However, a magma body may migrate to a new location or erupt at the surface before it completely solidifies. As a result, several types of igneous textures exist, including By definition, the crystals that make up aphanitic rocks are so small that individual minerals can be distinguished only with the aid of a polarizing microscope or other sophisticated techniques. Therefore, we commonly characterize fine-grained rocks as being light, intermediate, or dark in color. Using this system of grouping, light-colored aphanitic rocks are those containing primarily light-colored non-ferromagnesian silicate minerals. Phaneritic texture. When large masses of magma slowly crystallize at great depth, they form igneous rocks that exhibit a coarse-grained texture described as phaneritic. Coarse-grained rocks consist of a mass of intergrown crystals that are roughly equal in size and large enough to distinguish the individual minerals without the aid of a microscope. Geologists often use a small magnifying lens to aid in identifying minerals in a phaneritic rock. Porphyritic texture. A large mass of magma may require thousands or even millions of years to solidify. Because different minerals crystallize under different environmental conditions, it is possible for crystals of one mineral to become quite large before others even begin to form. If molten rock containing some large crystals moves to a different environment, for example, by erupting at the surface, the remaining liquid portion of the lava cools more quickly. The resulting rock, which has large crystals embedded in a matrix of smaller crystals, is said to have a porphyritic texture. The large crystals in porphyritic rocks are referred to as phenocrysts, whereas the matrix of smaller crystals is called groundmass. A rock with a porphyritic texture is termed a porphyry. Vesicular texture. Common features of many extrusive rocks are the voids left by gas bubbles that escape as lava solidifies. These nearly spherical openings are called vesicles, and the rocks that contain them are said to have a vesicular texture. Rocks that exhibit a vesicular texture often form in the upper zone of a lava flow, where cooling occurs rapidly enough to preserve the openings produced by the expanding gas bubbles. Another common vesicular rock, called pumice, forms when silica-rich lava is ejected during an explosive eruption. Glassy texture. During some volcanic eruptions, molten rock is ejected into the atmosphere, where it is quenched to become a solid. Rapid. Figure 4.8. Porphyritic texture. The large crystals in porphyritic rocks are called phenocrysts, and the matrix of smaller crystals is called groundmass. Vesicular texture. USGS Figure 4.9 Vesicular texture. The larger image shows a lava flow on Hawaii's Kilauea volcano. The inset photo is a close-up showing the vesicular texture of hardened lava. Vesicles are small holes left by escaping gas bubbles. Aphanitic, phaneritic, porphyritic, vesicular, glassy, pyroclastic, and pegmatitic. Aphanitic texture: igneous rocks that form at the surface or as small intrusive masses within the upper crust where cooling is relatively rapid exhibit a fine-grained texture termed aphanitic. Cooling of this type may generate rocks having a glassy texture. Glass results when unordered ions are frozen in place before they are able to unite into an orderly crystalline structure. Obsidian, a common type of natural glass, is similar in appearance to dark chunks of manufactured glass. Because of its excellent conchoidal fracture and ability to hold a sharp, hard edge, obsidian was a prized material from which Native Americans chipped arrowheads and cutting tools. Obsidian flows, typically a few hundred feet thick, provide evidence that rapid cooling is not the only mechanism that produces a glassy texture. Magmas with high silica content tend to form long, chain-like structures before crystallization is complete. These structures, in turn, impede ionic transport and increase the magma's viscosity. So, granitic magma, which is rich in silica, may be extruded as an extremely viscous mass that eventually solidifies to form obsidian. By contrast, basaltic magma, which is low in silica, forms very fluid lavas that, upon cooling, usually generate fine-grained crystalline rocks. However, when a basaltic lava flow enters the ocean, its surface is quenched rapidly enough to form a thin, glassy skin. Pyroclastic texture: another group of igneous rocks is formed from the consolidation of individual rock fragments ejected during explosive volcanic eruptions. The ejected particles might be very fine ash, molten blobs, or large angular blocks torn from the walls of a vent during an eruption. Igneous rocks composed of these rock fragments are said to have a pyroclastic texture, or fragmental texture. A common type of pyroclastic rock, called welded tuff, is composed of fine fragments of glass that remained hot enough to fuse together. Other pyroclastic rocks are composed of fragments that solidified before impact and became cemented together at some later time. Because pyroclastic rocks are made of individual particles or fragments rather than interlocking crystals, their textures often resemble those exhibited by sedimentary rocks rather than those associated with igneous rocks. Pegmatitic texture: under special conditions, exceptionally coarse-grained igneous rocks, called Figure 4.10 Obsidian arrowhead. Native Americans made arrowheads and cutting tools from obsidian, a natural glass. Photo by Jeffrey Scoville. Figure 4.11. Pyroclastic rocks are the product of explosive eruptions. These volcanic fragments may eventually consolidate to become rocks, displaying a pyroclastic texture. Photo by Richard Roscoe. Getty Images. Figure 4.12. Pegmatitic texture: this granite pegmatite, found in the inner gorge of the Grand Canyon, is composed mainly of quartz and feldspar. Pegmatites may form rocks of this type, in which most of the crystals are larger than 1 centimeter in diameter, are described as having a pegmatitic texture. Most pegmatites occur as small masses or thin veins within or around the margins of large intrusive igneous bodies. Pegmatites form late in the crystallization of a magma, when water and other materials, such as carbon dioxide, chlorine, and fluorine, make up an unusually high percentage of the melt. Because ion 4.4 Naming igneous rocks: distinguish among the common igneous rocks based on texture and mineral composition. Geologists classify igneous rocks on the basis of their texture and mineral composition. The various igneous textures described in the previous section result mainly from different cooling histories, whereas the mineral composition of an igneous rock depends on the chemical makeup of its parent magma. Because igneous rocks are classified on the basis of both mineral composition and texture, some rocks having similar mineral constituents but exhibiting different textures are given different names. Pele's hair, Marley Miller, Uskspiel's tears. These two types of hardened lava, called Pele's hair and Pele's tears, are commonly generated during lava fountaining that occurs at Kilauea volcano. They are named after Pele, the Hawaiian goddess of fire and volcanoes. Pele's hair consists of goldish strands that are created when tiny blobs of lava are stretched by strong winds. When lava droplets cool quickly, they form Pele's tears, which are sometimes connected to strands of Pele's hair. Question 1. What is the texture of Pele's hair and Pele's tears? Question 2. What kind of igneous rock is Pele's tears? Ion Earth 4.1. Granitic igneous rocks. Granite. Of all the igneous rocks, granite is perhaps the best known. This is because of its natural beauty, which is enhanced when it is polished, and its abundance in the continental crust. Slabs of polished granite are commonly used for tombstones and monuments and as building stones. Well-known areas in the United States where granite is quarried include Barre, Vermont, Mount Airy, North Carolina, and St. Cloud, Minnesota. Granite is a coarse-grained rock composed of about 10 to 20% quartz and roughly 50% feldspar. When examined close up, the quartz grains appear somewhat rounded in shape, glassy, and clear to gray in color. By contrast, feldspar crystals are generally white, gray, or salmon pink in color, and they are blocky or rectangular in shape. Other minor constituents of granite include: migration is enhanced in these fluid-rich environments. The crystals that form are abnormally large. Thus, the large crystals in pegmatites do not result from inordinately long cooling histories, rather, they are the consequence of a fluid-rich environment that enhances crystallization. The composition of most pegmatites is similar to that of granite. Thus, pegmatites contain large crystals of quartz, feldspar, and muscovite. However, some contain significant quantities of relatively rare and hence valuable elements, gold, tungsten, beryllium, and the rare earth elements that are used in modern high-technology devices, including cell phones and hybrid autos. 1. Define texture. 2. How does the rate of cooling influence crystal size? What other factors influence the texture of igneous rocks? 3. List the 6 major igneous rock textures. 4. Explain how the crystals in pegmatites are able to grow so large. 5. What does a porphyritic texture indicate about the cooling history of an igneous rock? 4.3 Concept checks. Smart Figure 4.13 Classification of igneous rocks. Igneous rocks are classified based on mineral composition and texture. IGNEOUSROCKCLASSIFICADIONCHART 118. Obsidian. Obsidian is a dark-colored glassy rock that usually forms when highly silica-rich lava cools quickly at Earth's surface. In contrast to the orderly arrangement of ions characteristic of minerals, the arrangement of ions in glass is unordered. Consequently, glassy rocks such as obsidian are not composed of minerals in the same sense as most other rocks. Although usually black or reddish-brown in color, obsidian has a chemical composition that is roughly equivalent to that of the light-colored igneous rock granite, not like dark rocks such as basalt. Obsidian's dark color results from small amounts of metallic ions in an otherwise relatively clear, glassy substance. If you examine a thin edge, obsidian will appear nearly transparent. Pumice. Pumice is a glassy volcanic rock with a vesicular texture that forms when large amounts of gas escape through silica-rich lava to generate a gray, frothy mass. In some samples, the voids are quite noticeable, whereas in others the pumice resembles fine shards of intertwined glass. Because of the large percentage of voids, many samples of pumice float when placed in water. Oftentimes, flow lines are visible in pumice, indicating that some movement occurred before solidification was complete. Moreover, pumice and obsidian can often be small amounts of dark silicates, particularly biotite and amphibole, and sometimes muscovite. Although the dark components generally make up less than 10% of most granites, dark minerals appear to be more prominent than their percentage indicates. At a distance, most granitic rocks appear gray in color. However, when composed of dark pink feldspar grains, granite can exhibit a reddish color. In addition, some granites have a porphyritic texture. These specimens contain elongated feldspar crystals a few centimeters in length that are scattered among smaller crystals of quartz and amphibole. Rhyolite is the fine-grained equivalent of granite and, like granite, is composed essentially of the light-colored silicates. This fact accounts for its color, which is usually buff to pink or occasionally light gray. Rhyolite is fine-grained and frequently contains glass fragments and voids, indicating that it cooled rapidly in a surface or near-surface environment. In contrast to granite, which is widely distributed as large intrusive masses, rhyolite deposits are less common and generally less voluminous. The thick rhyolite lava flows and extensive ash deposits in and around Yellowstone National Park are well-known exceptions to this generalization. Denistasa. Found in the same rock mass, where they exist in alternating layers. Andesitic igneous rocks. Andesite is a medium-gray, fine-grained rock typically of volcanic origin. Its name comes from South America's Andes Mountains, where numerous volcanoes are composed of this rock type. In addition, the volcanoes of the Cascade Range and many of the volcanic structures occupying the continental margins that surround the Pacific Ocean are of andesitic composition. Andesite commonly exhibits a porphyritic texture. See Figure 4. 13. When this is the case, the phenocrysts are often light, rectangular crystals of plagioclase feldspar or black, elongated amphibole crystals. Andesite may also resemble rhyolite, so its identification usually requires microscopic examination to verify mineral makeup. Diorite is the intrusive equivalent of andesite. It is a coarse-grained rock that looks somewhat like gray granite. However, it can be distinguished from granite because it contains little or no visible quartz crystals and has a higher percentage of dark silicate minerals. The mineral makeup of diorite is primarily plagioclase feldspar and amphibole. Because the light-colored feldspar grains and dark amphibole crystals appear to be roughly equal in abundance, diorite has a salt and pepper appearance. Basaltic igneous rocks. Basalt is a very dark green to black, fine-grained rock composed primarily of pyroxene and calcium-rich plagioclase feldspar, with lesser amounts of olivine and amphibole. Wenit. Figure 4.15. Pumice, a vesicular igneous rock. Most samples of pumice will float in water because they contain numerous vesicles. Volcano, Hawaii. Is porphyritic. Basalt commonly contains small, light-colored feldspar phenocrysts or green, glassy-appearing olivine grains embedded in a dark groundmass. Basalt is the most common extrusive igneous rock. Many volcanic islands, such as the Hawaiian Islands and Iceland, are composed mainly of basalt. Further, the upper layers of the oceanic crust consist of basalt. In the United States, large portions of central Oregon and Washington were the sites of extensive basaltic outpourings. At some locations, these once fluid basaltic flows have accumulated to a combined thicknesses approaching 3 kilometers. Gabbro is the intrusive equivalent of basalt. Like basalt, it tends to be dark green to black in color and composed primarily of pyroxene and calcium-rich plagioclase feldspar. Although gabbro is uncommon in the continental crust, it makes up a significant percentage of oceanic crust. Pyroclastic rocks. Pyroclastic rocks are composed of fragments ejected during a volcanic eruption. One of the most common pyroclastic rocks, called tuff, is composed mainly of tiny. Geographics 4.1. Granite, an intrusive igneous rock. To geologists, granite is an intrusive igneous rock with a rather precise mineral composition. However, the term granite is commonly used to describe a group of related rocks that are rich in quartz and feldspar. We will follow the latter convention here. Locations of granite outcrops. 1. Coast Range Bathlith, British Columbia. 2. Canadian Shield, Ontario, Canada. 3. Cadillac Mountain, Acadia National Park, Maine. 4. Cathedral Ledge State Park, White Mountains, New Hampshire. 5. Stone Mountain, Georgia. Where is granite found? This map shows the distribution of exposed granitic rocks in the United States, Canada, and Mexico. Granitic rocks labeled batholiths along the west coast are mainly Mesozoic in age. Those in the north-central United States and the Canadian Shield are intermixed with metamorphic rocks and are Precambrian, while the granitic rocks of the Appalachian Mountains are mostly of Paleozoic age. Alami images. William Helsel. Question. List at least 4 different uses for granite. Polished granite is popular for countertops because it is durable as well as aesthetically pleasing. However, in the stone trade the name granite is applied to almost every coarse-grained igneous rock. Black granite, for example, is usually the rock gabbro. Granite is used in large construction projects as a structural element and decorative facing or veneer. The Arlington Memorial Bridge, constructed mainly of concrete, is covered by a decorative granite veneer. Granite is commonly used for memorials and gravestones because of its resistance to chemical weathering. The Trenton Battle Monument commemorates the December 26, 1776 battle in which the Continental Army defeated the British forces in Trenton, New Jersey. What are the uses of granite? Granite is widely used as a building material for countertops or tiles, building stones, and memorials. Rock of Ages Granite Quarry, Barre, Vermont. Granite was originally quarried using handsaws and explosives to blast away slabs of rock. Today, saws with diamond chips embedded in steel wires and saw blades are used. Rock of Ages Granite Quarry, Barre, Vermont. Granite was originally quarried using handsaws and explosives to blast away slabs of rock. Today, saws with diamond chips embedded in steel wires and saw blades are used. Shutterstock. 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 John Grime. John Grime. This photo shows rock exposed at Hole in the Wall, California, which formed as a result of an explosive ash eruption about 18.5 million years ago. Question 1. Most of this rock is composed of tiny ash fragments. What name is given to rocks of this type? Question 2. What rock name is given to the dark fragment in the upper part of the photo? Ash-size fragments that were later cemented together. In situations where the ash particles remained hot enough to fuse, the rock is called welded tuff. Although welded tuff consists mostly of tiny glass shards, it may contain walnut-sized pieces of pumice and other rock fragments. Welded tuff deposits cover vast portions of previously volcanically active areas of the western United States. Some of these tuff deposits are: Close up. 1. List the 2 criteria by which igneous rocks are classified. 2. How are granite and rhyolite different? In what way are they similar? 3. Classify each of the following rocks by their mineral composition: gabbro, obsidian, granite, and andesite. 4. Describe each of the following in terms of composition and texture: diorite, rhyolite, and basalt porphyry. 5. In what way does tuff and volcanic breccia differ from other igneous rocks such as granite and basalt? 4.4 Concept checks. Hundreds of feet thick and extend for more than 100 kilometers from their source. Most formed millions of years ago as volcanic ash spewed from large volcanic structures, sometimes spreading laterally at speeds approaching 100 kilometers per hour. Early investigators of these deposits incorrectly classified them as rhyolite lava flows. Today, we know that silica-rich lava is too viscous to flow more than a few miles from a vent. Pyroclastic rocks, composed mainly of particles larger than ash, are called volcanic breccia. The particles in volcanic breccia may consist of streamlined lava blobs that solidified in air, blocks broken from the walls of the vent, ash, and glass fragments. Unlike most igneous rock names, such as granite and basalt, the terms tuff and volcanic breccia do not imply mineral composition. Instead, they are frequently identified with a modifier. For example, rhyolite tuff indicates a rock composed of ash-sized particles having a felsic composition. Melting temperature. When confining pressure drops sufficiently, decompression melting is triggered. Decompression melting occurs wherever hot, solid mantle rock ascends, thereby moving into regions of lower pressure. Recall from Chapter 2 that tensional forces along spreading centers promote upwelling where plates diverge. This process is responsible for generating magma along oceanic ridges where plates are rifting apart. Below the ridge crest, hot mantle rock rises and melts, generating a magma that replaces the material that shifted horizontally away from the ridge axis. Decompression melting also occurs when ascending mantle plumes reach the uppermost mantle. If this rising magma reaches the surface, it will trigger an episode of hotspot volcanism. Addition of water. An important factor affecting the melting temperature of rock is its water content. Water and other volatiles act as salt does to melt ice. That is, most magma originates in Earth's uppermost mantle. The greatest quantities are produced at divergent plate boundaries, in association with seafloor spreading, with lesser amounts forming at subduction zones, where oceanic lithosphere descends into the mantle. Magma also can be generated when crustal rocks are heated sufficiently to melt. Generating magma from solid rock. Workers in underground mines know that temperatures increase as they descend deeper below Earth's surface. Although the rate of temperature change varies considerably from place to place, it averages about 25 degrees Celsius per kilometer in the upper crust. This increase in temperature with depth is known as the geothermal gradient. As shown in Figure 4.18, when a typical geothermal gradient is compared to the melting point curve for the mantle rock peridotite, the temperature at which peridotite melts is higher than the geothermal gradient. Thus, under normal conditions, the mantle is solid. However, tectonic processes trigger melting through various means, including reducing the melting point of mantle rock. Decrease in pressure, decompression. Melting. If temperature were the only factor that determined whether rock melts, our planet would be a molten ball covered with a thin, solid outer shell. This is not the case because pressure, which also increases with depth, influences the melting temperatures of rocks. Melting, which is accompanied by an increase in volume, occurs at progressively higher temperatures with increased depth. This is the result of the steady increase in confining pressure exerted by the weight of overlying rocks. Conversely, reducing confining pressure lowers a rock's 4.5 origin of magma. Summarize the major processes that generate magma from solid rock. Based on evidence from the study of earthquake waves, we know that Earth's crust and mantle are composed primarily of solid, not molten, rock. Although the outer core is fluid, this iron-rich material is very dense and remains deep within Earth. So where does magma come from? Temperature 500, 150. Smart Figure 4.18. Why the mantle is mainly solid. This diagram shows the geothermal gradient for the crust and upper mantle. Also illustrated is the melting point curve for the mantle rock peridotite. Continental volcanic arc. 1. What is the geothermal gradient? Describe how the geothermal gradient compares with the melting temperatures of the mantle rock peridotite at various depths. 2. Explain the process of decompression melting. 3. What role do water and other volatiles play in the formation of magma? 4. Name 2 plate tectonic settings in which you would expect magma to be generated. 4.5 Concept checks. Lithosphere. Water causes rock to melt at lower temperatures, just as putting rock salt on an icy sidewalk induces melting. The introduction of water to generate magma occurs mainly at convergent plate boundaries, where cool slabs of oceanic lithosphere descend into the mantle. As an oceanic plate sinks, heat and pressure drive water from the subducting oceanic crust and overlying sediments. These fluids migrate into the wedge of hot mantle that lies directly above, at a depth of about 100 kilometers. The wedge of mantle rock is sufficiently hot that the addition of water leads to some melting. Partial melting of the mantle rock peridotite generates hot basaltic magma whose temperatures may exceed 1,250 degrees Celsius. Temperature increase, melting crustal rocks. As soon as mantle-derived basaltic magma forms, it will buoyantly rise toward the surface. In continental settings, basaltic magma often ponds beneath crustal rocks, which have a lower density and are already near their melting temperature. The hot basaltic magma may heat the overlying crustal rocks sufficient to generate a secondary, silica-rich magma. If these low-density, silica-rich magmas reach the surface, they tend to produce explosive eruptions that we associate with convergent plate boundaries. Crustal rocks can also melt during continental collisions that result in the formation of a large mountain belt. During these events, the crust is greatly thickened, and some crustal rocks are buried to depths where the temperatures are elevated sufficiently to cause partial melting. The felsic magmas produced in this manner usually solidify before reaching the surface, so volcanism is not typically associated with these collision-type mountain belts. In summary, magma can be generated three ways. A decrease in pressure can result in decompression melting. The introduction of water can lower the melting temperature of hot mantle rock sufficiently to generate magma. And heating of crustal rocks above their melting temperature produces magma. Figure 4.19. Decompression melting. As hot mantle rock ascends, it continually moves into zones of lower and lower pressure. This drop in confining pressure initiates decompression melting in the upper mantle. Figure 4.20. Water lowers the melting temperature of hot mantle rock to trigger partial melting. As an oceanic plate descends into the mantle, water and other volatiles are driven from the subducting crustal rocks into the mantle above. 4.6. How magmas evolved. Describe how magmatic differentiation can generate a magma body that has a mineralogy that is different from its parent magma. Geologists have observed that, over time, a volcano may extrude lavas that vary in composition. Data of this type led them to examine the possibility that magma might change, and thus one magma body could become the parent to a variety of igneous rocks. To explore this idea, N. L. Bowen carried out a pioneering investigation into the crystallization of magma early in the 20th century. Bowen's reaction series and the composition of igneous rocks. Recall that ice freezes at a specific temperature, whereas basaltic magma crystallizes over a range of at least 200 degrees Celsius of cooling. In a laboratory setting, Bowen and his co-workers demonstrated that as a basaltic magma cools, minerals tend to crystallize in a systematic fashion, based on their melting temperatures. As shown in Figure 4.21, the first mineral to crystallize is the ferromagnesian mineral olivine. Further cooling generates calcium-rich plagioclase feldspar as well as pyroxene, and so forth down the diagram. During this crystallization process, the composition of the remaining liquid portion of the magma also continually changes. For example, at the stage when about 1/3 of the magma has solidified, the remaining molten material will be nearly depleted in iron, magnesium, and calcium because these elements are major constituents of the minerals that form earliest in the process. The absence of these elements causes the melt to become enriched in sodium and potassium. Further, because the original basaltic magma contained about 50% silica, the crystallization of the earliest formed mineral, olivine, which is only about 40% silica, leaves the remaining melt richer in CO. Thus, the silica component of the remaining melt becomes enriched as the magma evolves. Bowen also demonstrated that if the solid components in a magma remain in contact with the remaining melt, they will chemically react and change mineralogy. As shown in Figure 4.21, for this reason, this order of mineral formation became known as Bowen's reaction series. However, in nature, the earliest formed minerals can separate from the melt, thus halting any further chemical reaction. The diagram of Bowen's reaction series in Figure 4.21 depicts the sequence in which minerals crystallize from a magma of basaltic composition under laboratory conditions. Evidence that this highly idealized crystallization. BOWENSREACTIONSERIES. Figure 4.21 Bowen's reaction series. This diagram shows the sequence in which minerals crystallize from a mafic magma. Compare this figure to the mineral composition of the rock groups in Figure 4.13. Note that each rock group consists of minerals that crystallize in the same temperature range. Figure 4.22. Crystal settling results in a change in the composition of the remaining melte. Magma evolves as the earliest formed minerals crystallize and settle to the bottom of the magma chamber, leaving the remaining melt richer in sodium, potassium, and silica. Figure 4.23. The Palisades Sill. As seen from New York City, the Palisades form impressive cliffs along the west side of the Hudson River for more than 80 kilometers. This structure, which is visible from Manhattan, formed when magma was injected between layers of sandstone and shale. Therese Loeb. Kreuzerl Lamy. Crystallization of magma, a separation of various components, can occur. One mechanism that causes this to happen is called crystal settling. This process occurs when the earlier formed minerals are denser than the liquid portion and sink toward the bottom of the magma chamber, as shown in Figure 4.22. When the remaining melt solidifies, either in place or in another location, if it migrates into fractures in the surrounding rocks, it will form a rock with a mineral composition that is different than the parent magma. The formation of a magma body having a mineralogy or chemical composition that is different than the parent magma is called magmatic differentiation. A classic example of magmatic differentiation is found in the Palisades Sill, which is a 300-meter thick slab of dark igneous rock exposed along the west bank of the lower Hudson River across from New York City. Because of its great thickness and magma having a MAC composition erupts UID basaltic lavas. The remaining melt will be enriched with silica, and should a subsequent eruption occur, the rocks generated will be more silica-rich and closer to the felsic end of the compositional range than the initial magma. Cooling of the magma body causes crystals of olivine, pyroxene, and calcium-rich plagioclase to form and settle out, or crystallize along the magma body's cool margins. MAC magma body. Fluid basaltic lava al. Olivine pyroxene. Calcium-rich plagioclase. Explosive eruption of silica-rich magma. Magma. Magma solid rock. Model approximates what can happen in nature comes from analysis of igneous rocks. In particular, scientists note that minerals that form in the same general temperature regime depicted in Bowen's reaction series are found together in the same igneous rocks. For example, notice in Figure 4.21 that the minerals quartz, potassium feldspar, and muscovite, which are located in the same region of Bowen's diagram, are typically found together as major constituents of the intrusive igneous rock granite. Magmatic differentiation and crystal settling. Bowen demonstrated that minerals crystallize from magma in a systematic fashion. But how do Bowen's findings account for the great diversity of igneous rocks? It has been shown that, at one or more stages during the 1. Define Bowen's reaction series. 2. How does the crystallization and settling of the earliest formed minerals affect the composition of the remaining magma? 3. Compare the processes of assimilation and magma mixing. 4.6 Concept checks. Recent studies indicate that the Palisades Sill was produced by multiple injections of magma and does not represent a simple case of crystal settling. However, it is nonetheless an instructional example of that process. As magma rises through Earth's brittle upper crust, it may dislodge and incorporate the surrounding host rocks. Melting of these blocks, a process called assimilation, changes the overall composition of the rising magma body. Figure 4.24. Assimilation of the host rock by a magma body. The composition of magma changes when the molten mass incorporates pieces of surrounding host rock, in a process called assimilation. During the ascent of two chemically distinct magma bodies, the more buoyant mass may overtake the slower rising body. Once joined, convective will mix the two magmas, generating a mass that is a blend of the two magma bodies. Figure 4.25. Magma mixing. This is one way the composition of a magma body can change. Subsequent slow rate of solidification, crystals of olivine can make up about 25% of the lower portion of the Palisades Sill. By contrast, near the top of this igneous body, where the last melt crystallized, olivine represents only 1% of the rock mass. Assimilation and magma mixing. Bowen successfully demonstrated that through magmatic differentiation, a single parent magma can generate several mineralogically different igneous rocks. However, more recent work indicates that magmatic differentiation involving crystal settling cannot, by itself, account for the entire compositional spectrum of igneous rocks. Once a magma body forms, the incorporation of foreign material can also change its composition. For example, in near-surface environments where rocks are brittle, the magma pushing upward can cause numerous fractures in the overlying rock. The force of the injected magma is often sufficient to dislodge and incorporate the surrounding host rock. Melting of these blocks, a process called assimilation, changes the overall chemical composition of the magma body. Another means by which the composition of magma can be altered is called magma mixing. Magma mixing may occur during the ascent of two chemically distinct magma bodies as the more buoyant mass overtakes the more slowly rising body. Once they are joined, convective flow stirs the two magmas, generating a single mass that has an intermediate composition. Smart Figure 4.26 Partial melting generates a magma that is nearer the felsic end of the compositional spectrum than the parent rock from which it was derived. https goo.gls5vigs 4.7 Partial melting and magma composition describe how partial melting of the mantle rock peridotite can generate a basaltic magma. Recall that igneous rocks are composed of a mixture of minerals and, therefore, tend to melt over a temperature range of at least 200 degrees Celsius. As rock begins to melt, the minerals with the lowest melting temperatures are the first to melt. If melting continues, minerals with higher melting points begin to melt, and the composition of the melt steadily approaches the overall composition of the rock from which it was derived. Most often, however, melting is not complete. The incomplete melting of rocks is known as partial melting, a process that produces most magma. Recall from Bowen's reaction series that rocks with a granitic composition are composed of minerals with the lowest melting temperatures, namely, quartz and potassium feldspar. Also note that as we move up Bowen's reaction series, the minerals have progressively higher melting temperatures and that olivine, which is found at the top, has the highest melting point. When a rock undergoes partial melting, it will form a melt that is enriched in ions from minerals with the lowest melting temperatures, while the unmelted portion is composed of minerals with higher melting temperatures. Separation of these two fractions yields a melt with a chemical composition that is richer in silica and nearer the felsic end of the spectrum than the rock from which it formed. In general, partial melting of ultramafic rocks tends to yield mafic magmas, partial melting of mafic rocks generally yields intermediate magmas, and partial melting of intermediate rocks can generate felsic magmas. Formation of basaltic magma. Most magma that erupts at Earth's surface is basaltic in composition and falls in a temperature range of 1000 degrees to 1250 degrees Celsius. Experiments show that under the high-pressure conditions calculated for the upper mantle, partial melting of the ultramafic rock peridotite can generate a magma of basaltic composition. Further evidence that many basaltic magmas have a mantle source are the inclusions of the rock peridotite, which basaltic magmas often carry up to Earth's surface from the mantle. Basaltic magmas that originate from partial melting of mantle rocks are called primary or primitive magmas because they have not yet evolved. Recall that partial melting that produces mantle-derived magmas may be triggered by a reduction in confining pressure during the process of decompression melting. This can occur, for example, where hot mantle rock ascends as part of slow-moving convective flow at mid-ocean ridges. Basaltic magmas are also generated at subduction zones, where water driven from the descending slab of oceanic crust promotes partial melting of the mantle rocks that lie above. Formation of andesitic and granitic magmas. If partial melting of mantle rocks generates most basaltic magmas, what is the source of the magma that crystallizes to form andesitic and granitic rocks? Recall that silica-rich magmas erupt mainly along the continental margins. This is strong evidence that continental crust, which is thicker and has a lower density than oceanic crust, must play a role in generating these more highly evolved magmas. One way andesitic magma can form is when a rising mantle-derived basaltic magma undergoes magmatic differentiation as it slowly makes its way through the continental crust. Recall from our discussion of Bowen's reaction series that as basaltic magma solidifies, the silica-poor ferromagnesian minerals crystallize first. If these iron-rich components are separated from the key partial melting of a hypothetical rock composed of the minerals on Bowen's reaction series yields two products. A melt having an intermediate to felsic composition. An unmelted residue having a matte composition. Olivine quartz. Plagioclase feldspar potassium, feldspar pyroxene amphibole. Liquid by crystal settling, the remaining melt will have an andesitic composition. Andesitic magmas can also form when rising basaltic magmas assimilate crustal rocks that tend to be silica-rich. Partial melting of basaltic rocks is yet another way in which at least some andesitic magmas are thought to be produced. Although granitic magmas can be formed through magmatic differentiation of andesitic magmas, most granitic magmas probably form when hot basaltic magma ponds. Below continental crust. When the heat from the hot basaltic magma partially melts the overlying crustal rocks, which are silica-rich and have a much lower melting temperature, the result can be the production of large quantities of granitic magmas. This process is thought to have been responsible for the volcanic activity in and around Yellowstone National Park in the distant past. 1. Briefly describe why partial melting results in a magma having a composition different from the rock from which it was derived. 2. How are most basaltic magmas thought to have formed? 3. What is the process that is thought to generate most granitic magmas? 4.7 Concept checks. Vent. Conduit. Atmosphere. Continental crust. Lithosphere. Asthenosphere. Magma chamber. Partial melting of continental crust generates magma with a granitic composition. Basaltic magma ponds beneath less dense crustal rocks. Basaltic magma buoyantly rises through lithospheric mantle. Partial melting of peridotite generates basaltic magma. 4.8 Intrusive igneous activity. Compare and contrast these intrusive igneous structures: dikes, sills, batholiths, stocks, and laccoliths. Although volcanic eruptions can be violent and spectacular events, most magma is in-placed and crystallizes at depth, without fanfare. Therefore, understanding the igneous processes that occur deep underground is as important to geologists as studying volcanic events. Nature of intrusive bodies. When magma rises through the crust, it forcefully displaces pre-existing crustal rocks, termed host rock or country rock. The structures that result from the emplacement of magma into pre-existing rocks are called intrusions, or plutons. Because all intrusions form far below Earth's surface, they are studied primarily after uplifting and erosion have exposed them. The challenge lies in reconstructing the events that generated these structures in vastly different conditions deep underground. Millions of years ago, intrusions are known to occur in a great variety of sizes and shapes. Some of the most common types are illustrated in Figure 4.28. Notice that some plutons have a tabular shape, whereas others are best described as massive. Also, observe that some of these bodies cut across existing structures, such as sedimentary strata, whereas others form when magma is injected between sedimentary layers. Because of these differences, intrusive igneous bodies are generally classified according to their shape, as either tabular or massive, and by their orientation with respect to the host rock. Igneous bodies are said to be discordant if they cut across existing structures and concordant if they inject parallel to features such as sedimentary strata. Smart Figure 4.27 Formation of granitic magma. Granitic magmas are generated by the partial melting of continental crust. Smart Figure 4.28 Intrusive igneous structures. Interrelationship between volcanism and intrusive igneous activity. B. Basic intrusive structures, some of which have been exposed by erosion. 4.8 Intrusive igneous activity. Tabular intrusive bodies, dikes and sills. Dikes and sills. Tabular intrusive bodies are produced when magma is forcibly injected into a fracture or zone of weakness, such as a bedding surface. Dikes are discordant bodies that form when magma is forcibly injected into fractures and cut across bedding surfaces and other structures in the host rock. By contrast, sills are nearly horizontal, concordant bodies that form when magma exploits weaknesses between sedimentary beds or other rock structures. In general, dikes serve as tabular conduits that transport magma upward, whereas sills tend to accumulate magma and increase in thickness. Dikes and sills are typically shallow features, occurring where the country rocks are sufficiently brittle to fracture. They can range in thickness from less than 1 mm to more than 1 km. While dikes and sills can occur as solitary bodies, dikes tend to form in roughly parallel groups called dike swarms. These multiple structures reflect the tendency for fractures to form in sets when tensional forces pull apart brittle country rock. Dikes can also radiate from an eroded volcanic neck, like spokes on a wheel. In these situations, the active ascent of magma generated fissures in the volcanic cone out of which lava flowed. Dikes frequently are more resistant and thus weather more slowly than the surrounding rock. Consequently, when exposed by erosion, dikes tend to have a wall-like appearance, as shown in Figure 4.30. Because dikes and sills are relatively uniform in thickness and can extend for many kilometers, they are assumed to be the product of very fluid, and therefore mobile, magmas. One of the largest and most studied of all sills in the United States is the Palisades Sill. Exposed for 80 kilometers along the west bank of the Hudson River in southeastern New York and northeastern New Jersey, the sill is about 300 meters thick. Because it is resistant to erosion, the Palisades Sill forms an imposing cliff that can be easily seen from the opposite side of the Hudson. Columnar jointing in many respects, sills closely resemble buried lava flows. Both are tabular and can. Sill. 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 Smart Figure 4.29 Sill exposed in Sinbad Country, Utah. The dark, essentially horizontal band is a sill of basaltic composition that intruded horizontal layers of sedimentary rock. Photo by Michael Collier. Extend over a wide area, and both may exhibit columnar jointing. Columnar jointing occurs when igneous rocks cool and develop shrinkage fractures that produce elongated, pillar-like columns that most often have 6 sides. Smart Figure 4.30 Dike exposed in the Spanish Peaks, Colorado. This wall-like dike is composed of igneous rock that is more resistant to weathering than the surrounding material. Rock. Today we know that large batholiths are produced by hundreds of discrete injection of magma that form smaller intrusive bodies that intimately crowd against or penetrate one another. These bulbous masses are emplaced over spans of millions of years. The intrusive activity that created the Sierra Nevada batholith, for example, occurred nearly continuously over a 130 million year period that ended about 80 million years ago. By definition, a plutonic body must have a surface exposure greater than 100 square kilometers to be considered a batholith. Smaller plutons are termed stocks. However, many stocks appear to be portions of much larger intrusive bodies that would be classified as batholiths if they were fully exposed. Emplacement of batholiths. How did massive granitic batholiths come to reside within sedimentary and metamorphic rocks that are only moderately deformed? What happened to the rock that was displaced by these huge igneous masses? How do magma bodies make their way through several kilometers of solid rock? Geologists continue to study and debate these questions. We know that magma rises because it is less dense than the surrounding rock, much as a cork held at the bottom of a container of water will rise when it is released. In the upper mantle and lower crust, where temperatures and pressures are high, rock is ductile. In this setting, buoyant magma bodies. Further, because sills and dikes generally form in near-surface environments and may be only a few meters thick, the emplaced magma often cools quickly enough to generate a fine-grained texture. Massive intrusive bodies, batholiths, stocks, and laccoliths. Batholiths. By far the largest intrusive igneous bodies are batholiths. Batholiths occur as mammoth linear structures several hundred kilometers long and up to 100 kilometers wide. The Sierra Nevada batholith, for example, is a continuous granitic structure that forms much of the backbone of the Sierra Nevada in California. An even larger batholith extends for over 1,800 kilometers along the coast mountains of western Canada and into southern Alaska. Although batholiths can cover a large area, recent geophysical studies indicate that most are less than 10 kilometers thick. Some are even thinner, The coastal batholith of Peru, for example, is essentially a flat slab with an average thickness of only 2 to 3 kilometers. Batholiths are typically composed of felsic and intermediate rock types and are often called granite batholiths. Early investigators thought the Sierra Nevada batholith was a huge single body of intrusive igneous. Figure 4.31 Columnar jointing on Akan Island located in the Aleutian Islands, Alaska. Some of the host rock that was displaced will fill in the space left by the magma body as it passes. As a magma body nears the surface, it encounters relatively cool, brittle country rock that is not easily pushed aside. Further upward movement may be accomplished by a process called stoping, in which blocks of the roof overlying a hot, rising mass become dislodged and sink through the magma. Evidence supporting stoping is found in plutons that contain suspended blocks of country rock called xenoliths. Magma may also melt and assimilate some of the overlying host rock. However, this process is greatly limited by the available thermal energy contained in the magma body. When plutons are placed near the surface, the room problem may be solved by lifting the roof that overlies the intrusive body. Laccoliths. A 19th century study by G. K. Gilbert of the U.S. Geological Survey in the Henry. An analogous situation occurs when a can of oil-based paint is left in storage. The oily component of the paint is less dense than the pigments used for coloration, thus, oil collects into drops that slowly migrate upward, while the heavier pigments settle to the bottom. Coast Range batholith. Idaho batholith. Pacific Ocean. Sierra Nevada batholith. Southern California batholith. Figure 4.32. Granitic batholiths along the western margin of North America. These gigantic, elongated bodies consist of numerous plutons that were placed beginning about 150 million years ago. Are assumed to rise in the form of diapirs, invertetrad-drop-shaped masses with rounded heads and tapered tails. However, in the upper crust, large dike-like structures may provide conduits for the ascent of magma. Depending on the tectonic environment, several mechanisms have been proposed to solve the room problem. At great depths, where rock is ductile, a mass of buoyant, rising magma can forcibly make room for itself by pushing aside the overlying rock, a process called shouldering. As the magma continues to move upward. Figure 4.33. Xenoliths are inclusions of host rock contained within igneous bodies. This unmelted chunk of dark rock was incorporated into a granitic magma, eastern Sierra Nevada, Rock Creek Canyon, California. 1. What is meant by the term country rock? 2. Describe dikes and sills, using the appropriate terms from the following list: massive, discordant, tabular, and concordant. 3. Distinguish among batholiths, stocks, and laccoliths in terms of size and shape. 4.8 Concept checks. Shiprock, New Mexico, is an igneous structure that rises more than 510 meters above the surrounding desert in northwestern New Mexico. It consists of rock that accumulated in the vent of a volcano that has since been eliminated by erosion. Photo by Michael Collier. Question 1. What type of landform is shiprock? Question 2. What type of structure is the long, narrow ridge extending away from shiprock? Eye on Earth 4.3. Figure 4.34. Laccoliths. Mount Ellen in Utah's Henry Mountains is one of 5 peaks that make up this small mountain range. Although the main intrusions in the Henry Mountains are stocks, numerous laccoliths formed as offshoots of these structures. Photo by Michael DeFreitas. North America Alamy. Mountains of Utah produced the first clear evidence that igneous intrusions can lift the sedimentary strata they penetrate. Gilbert named the igneous intrusions he observed laccoliths, which he envisioned as igneous rock forcibly injected between sedimentary strata, so as to arch the beds above while leaving those below relatively flat. It is now known that the 5 major peaks of the Henry Mountains are not laccoliths but stocks. However, these central magma bodies are the source material for branching offshoots that are true laccoliths, as Gilbert defined them. Numerous other granitic laccoliths have since been identified in Utah. The largest is a part of the Pine Valley Mountains located north of St. George, Utah. Others are found in the La Salle Mountains near Arches National Park and in the Abajo Mountains directly to the south. 4 concepts in review: magma, igneous rocks, and intrusive activity. 4.1 Magma, parent material of igneous rock. List and describe the 3 major components of magma. Key terms: igneous rock, magma, lava, melt, volatile, crystallization, intrusive igneous rock, extrusive igneous rock. Completely or partly molten rock is called magma if it is below Earth's surface, and lava if it has erupted onto the surface. It consists of a liquid melt with possible additions of solids and gases, such as water vapor or carbon dioxide. 4.2 Igneous compositions. Compare and contrast the 4 basic igneous compositions: basaltic, granitic, andesitic, and ultramafic. Key terms: granitic composition, basaltic composition, andesitic composition, peridotite, ultramafic. Igneous rocks are composed mostly of silicate minerals. If a given igneous rock is mostly composed of non-ferromagnesian minerals, it is described as felsic. If the rock has a greater proportion of ferromagnesian minerals, it may be classified as mafic. Mafic rocks are generally darker in color and of greater density than their felsic counterparts. Broadly, continental crust is felsic in composition, and oceanic crust is mafic. As magma cools, silicate minerals begin to form from the cocktail of mobile ions in the melt. These tiny crystals grow through the addition of ions to their outer surface. As cooling proceeds, crystallization gradually transforms the magma into a solid mass of interlocking crystals, an igneous rock. Magmas that cool below the surface produce intrusive igneous rocks, whereas those that erupt onto Earth's surface produce extrusive igneous rocks. Intermediate rocks in which plagioclase feldspar predominates are compositionally between felsic and mafic. They are typical of continental volcanic arcs. Ultramafic rocks, which are rich in the minerals olivine and pyroxene, dominate in the upper mantle. The amount of silica in an igneous rock is an indication of its overall composition. Rocks that contain a lot of silica are felsic, while rocks that are poor in silica fall on the ultramafic end of the spectrum. The amount of silica present in a magma determines both its viscosity and its crystallization temperature. Q. Describe igneous rocks having the compositions of samples A and D, using terms such as mafic, felsic, etc. Would you ever expect to find quartz and olivine in the same rock? Why or why not? 4.3 Igneous textures, what can they tell us? Identify and describe the 6 major igneous textures. Key terms: texture, aphanitic, phaneritic, porphyritic texture, phenocryst, groundmass, porphyry, vesicular texture, glassy texture, pyroclastic texture, pegmatite, pegmatitic texture. To geologists, texture is a description of the size, shape, and arrangement of mineral grains in a rock. Careful observation of the texture of igneous rocks can tell us about the conditions under which they formed. The rate at which magma or lava cools is an important factor in the rock's final texture. 4.4 Naming igneous rocks. Distinguish among the common igneous rocks based on texture and mineral composition. Key terms: granite, rhyolite, obsidian, pumice, andesite, diorite, basalt, gabbro, pyroclastic rocks. Igneous rocks are classified on the basis of their textures and their compositions. Figure 4.13 summarizes the naming system based on 4.6 How magmas evolve. Describe how magmatic differentiation can generate a magma body that has a mineralogy that is different from its parent magma. Key terms: Bowen's reaction series, crystal settling, magmatic differentiation, assimilation, magma mixing. Pioneering experimentation by N. Eld Bowen revealed that in a cooling magma, minerals crystallize in a specific order. Ferromagnesian silicates. The cooling rate is quick for lava at or close to the surface, so crystallization is rapid and results in a large number of very small crystals. The result is a fine-grained texture. Magma cooling at depth loses heat more slowly. This allows sufficient time for the magma's ions to be organized into larger crystals, resulting in a rock with a coarse-grained texture. If crystals begin to form at depth and then the magma moves to a shallow depth or erupts at the surface, it will have a two-stage cooling history. The result is a rock with a porphyritic texture. Volcanic rocks may exhibit additional textures: vesicular if they had a high gas content, glassy if they were high in silica, pyroclastic if they erupted explosively. The large crystals that characterize pegmatitic textures result from the crystallization of magmas with high water content. These two criteria. Two magmas with the same composition can cool at different rates, resulting in different final textures. On the other hand, two magmas that have different compositions may attain similar textures if they cool under similar circumstances. Q. Could granite ever be transformed into a rhyolite? If so, what processes would have to be involved? 4.5 Origin of magma. Summarize the major processes that generate magma from solid rock. Key terms: geothermal gradient, decompression, melting. Solid rock may melt under three geologic circumstances: when heat is added to the rock, raising its temperature; when already hot rock experiences lower pressures; and when water is added. Q. Different processes produce magma in different tectonic settings. Consider situations A, B, and C in the diagram and describe the processes that would be most likely to trigger melting in each. Such as olivine crystallize first, at the highest temperatures, and non-ferromagnesian silicates such as quartz crystallize last, at the lowest temperatures. Bowen found that in between these temperatures, chemical reactions take place between the crystallized silicates and the melt, resulting in compositional changes to each and the formation of new minerals. Various physical processes can cause changes in the composition of magma. For instance, if crystallized silicates are denser than the remaining magma, they will sink to the bottom of the magma chamber, because these early formed minerals are likely to be mostly quartz and potassium feldspar, plagioclase feldspar, amphibole, and biotite, pyroxene and olivine. Ferromagnesians, the magma has now differentiated toward a more felsic composition. As they migrate, magmas may react with their host rocks or with other magma bodies. Assimilation of host rock or magma mixing will alter the magma's composition. Q. Consider the accompanying diagram, which shows a cross-sectional view of a hypothetical magma chamber. Using your understanding of Bowen's reaction series and magma evolution, interpret the layered structure by explaining how crystallization occurred. 4.7 Partial melting and magma composition. Describe how partial melting of the mantle rock peridotite can generate a basaltic magma. Key term: partial melting. In most circumstances, when rocks melt, they do not melt completely. Different minerals have different temperatures at which they change state from solid to liquid. As rocks melt, minerals with the lowest melting temperatures melt first. Partial melting of the ultramafic mantle yields mafic oceanic crust. Partial melting of the lower continental crust at subduction zones produces magmas that have intermediate or felsic compositions. Q. If all silicate minerals melted at exactly the same temperature, would magmas of different compositions exist? How is partial melting important for generating the different kinds of rocks on Earth? 4.8 Intrusive igneous activity. Compare and contrast these intrusive igneous structures: dikes, sills, batholiths, stocks, and laccoliths. Key terms: host rock, intrusion, tabular, massive, discordant, concordant, dike, sill, columnar jointing, batholith, stock, xenolith, laccolith. When magma intrudes other rocks, it may cool and crystallize before reaching the surface to produce intrusions called plutons. Plutons come in many shapes. They may cut across the host rocks without regard for pre-existing structures, or the magma may flow along weak zones in the host rock, such as between the horizontal layers of sedimentary bedding. Tabular intrusions may be concordant or discordant. Massive plutons may be small or very large. Blister-like intrusions also exist. As solid igneous rock cools, its volume decreases. Contraction can produce a distinctive fracture pattern called columnar jointing. Several processes contribute to magma's intrusion into host rocks. Rising diapirs are one possibility, and another is shouldering a side of host rocks. Stoping of xenoliths from the host rock can open up more room, or the magma can melt and assimilate some of the host rock. Q. Create a sketch, including labels, showing a series of igneous intrusions into sedimentary rocks. Include a dike, a sill, a stock, a batholith, a laccolith, some xenoliths, and a diapir. 3. Is it possible for two igneous rocks to have the same mineral composition but be different rocks? Use an example to support your answer. 4. Use figure 4.5 to classify the following igneous rocks. An aphanitic rock containing about 30% calcium-rich plagioclase feldspar, 55% pyroxene, and 15% olivine. B. The phaneritic rock containing about 20% quartz, 40% potassium feldspar, 20% sodium-rich plagioclase feldspar, a few percent muscovite, and the remainder dark-colored silicate. C. An aphanitic rock containing about 50% plagioclase feldspar, 35% amphibole, 10% pyroxene, and minor amounts of other light-colored silicates. D. A phaneritic rock made mainly of olivine and pyroxene, with lesser amounts of calcium-rich plagioclase feldspar. 5. Identify the igneous rock textures described by each of the following statements. A. Openings produced by escaping gases. B. The texture of obsidian. C. The matrix of fine crystals surrounding phenocrysts. D. Consists of crystals that are too small to be seen without a microscope. E. A texture characterized by rock fragments welded together. F. Coarse-grained, with crystals of roughly equal size. G. Exceptionally large crystals, most exceeding 1 cm in diameter. 7. A common misconception about Earth's upper mantle is that it is a thick shell of molten rock. Explain why Earth's mantle is actually solid under most conditions. 8. Describe two mechanisms by which mantle rock can melt without an increase in temperature. How do these magma-generating mechanisms relate to plate tectonics? 9. Use your understanding of Bowen's reaction series to explain how partial melting can generate magmas that have different compositions. 10. During a field trip with your geology class, you visit an exposure of rock layers similar to the one sketched here. A fellow student suggests that the layer of basalt is a sill. You disagree. Why do you think the other student is incorrect? What is a more likely explanation for the basalt layer? 6. During a hike, you pick up the igneous rock shown in the accompanying photo. What is the mineral name of the small, rounded, glassy green crystals? B. Did the magma from which this rock formed likely originate in the mantle or in the crust? Explain. C. Was the magma likely a high-temperature magma or a low-temperature magma? Explain. D. Describe the texture of this rock. Shale, basalt, sandstone, shale, vesicles. Give it some thought. 1. Would you expect all the crystals in an intrusive igneous rock to be the same size? Explain why or why not. 2. Apply your understanding of igneous rock textures to describe the cooling history of each of the igneous rocks pictured here. Photos by E.E.J. Tarbuck. Give it some thought. Looking for additional review and test prep materials? With individualized coaching on the toughest topics of the course, Mastering Geology offers a wide variety of ways for you to move beyond memorization to begin thinking like a geologist. Visit the study area and to find practice quizzes, study tools, and multimedia that will improve your understanding of this chapter's content. Sign in today to enjoy the following features: self-study quizzes, smart figures, tutorials, animations, Condor videos, mobile field trips, Geoscience Animation Library, Geode, RSS feeds, digital study modules, and an optional Pearson eText. 11. Each of the following statements describes how an intrusive feature appears when exposed at Earth's surface due to erosion. Name each feature. A dome-shaped mountainous structure flanked by upturned layers of sedimentary rocks. B. A vertical wall-like feature a few meters wide and hundreds of meters long. C. A huge expanse of granitic rock forming a mountainous terrain tens of kilometers wide. D. A relatively thin layer of basalt sandwiched between horizontal layers of sedimentary rocks exposed along the walls of a river valley. 12. Mount Whitney, the highest summit in the contiguous United States, is located in the Sierra Nevada batholith. Based on its location, is Mount Whitney likely composed mainly of granitic, andesitic, or basaltic rocks? Photo by John Grine. Getty Images.